Hello friends, welcome again to this channel. Today let me give you an example where we can use the idea or the principle of per unit system. For instance, we have here the circuit system in which we have a generator, four transformer, namely T1, T2, T3, and T4, and we have here also a motor and a load. In each equipment we have a specific values. For instance, we have here for the generator 90 megavolt amperes at 22 kV, where X is 18%, and for T1 we have 50 MVA 22 over 220 kV. So T1 is 22 over 220 kV. The X here is 10%. So also with T2 and T3 and T4 transformers. And for the motor you have 66.5 MVA, okay, and at 10.54 kV the X is 18.5%. and for the load you have 57 MVA, 0.6 power factor lead. It means that this load is more capacitive. And for your transmission you have line 1 and line 2. For line 1 you have 48.4 ohms, and for line 2 you have 68.43 ohms. We will choose base value, so we choose an apparent power base. For me, I will choose a 100 MVA. So you can choose any of the MVA value, any value will go, but for me I think what's best is the 100 MVA. Now for the voltage base, I choose also the first voltage on the primary side of T1, which is also the voltage of the generator, which is 22 kV. So the base voltage will change along the circuit system, but the apparent power base is constant. It will be used all throughout the system. So the base voltage, the one that we can use to have the system apply sectioning. For instance, in this part, so this will be 22 kV. By the way, this is the bus bar for the generator side, and the transformer 1 primary side, that is 22 kV here. And for the transformer 3, it's also 22. So this part is the section in which 22 kV is the base voltage. And for the here for the line 1, you see that in the transformer 1 secondary side is 220, so this part. And for the transformer 2, you have also the primary side of 220 kV, and the secondary is 11. So the line 1 voltage base is 220, so this is another section. And another section is the secondary side of the transformer 2. Okay, transformer 2 is 220 over 11 kV, so the secondary side is 11 kilovolt. So for the transformer 4, you have also 11 kilovolt. So here, this section, and also for the motor and the load, this covers the selected base voltage, which is 11 kV. And also for the line 2, so line 2 here, for the transformer 4, the primary side is 110 kV, and for the transformer 3 you have also 110. So this is another section for the line 2, 110 kV. So you have 1, 2, 3, and 4 sections separated by the chosen base voltage. And for each given here, we can right away get the old per unit. Okay, for instance, here in our generator, it is given here the 18% for the reactant, so this will be 0.18. so this will now be used as the X per unit old of our G. For our transformer, we have here 10%, so this can be divided into 100, that is 0.1, so T1. the X per unit of T1 is 0.1, and for T2 you have 0.06, for T3 you have 0.064, for T4 you have 0.08, and for your motor 18.5%, which can be also divided by 100, which is 0.185. And we are going to get also for the load, and for the line 1 and for the line 2. This is how you set up the system for us to apply the per unit concept. And now let us get the new per unit value of the generator. We have given here the old 0.18, so we use this general formula that the new per unit is equals to the old per unit multiplied by the base apparent power base new divided by apparent power base old, multiplied by the voltage base old divided by the voltage base new squared. And here are the different per unit value in which we can directly get by just substitution. For instance, we have for here the generator, the old is 0.18 from 18%, so you just place it here, so you have 0.18, and the new base we have already selected 100 MVA for the whole system divided by the old is 90, so 100 over 90. And for the base voltage old, that will be 22 kV. And for the new, we have here the new voltage that is 22 also, so you just divide that's equal to 1 and squared it, so you compute, and then it will give you the new generator X per unit is 0.2 per unit. And for the transformer, we have also the old, which is 0.1, and the new again is 100 MVA divided by 50, which is the old. And the old voltage here is 22, okay, and 22, and also divided by the new voltage, which is 22, so that's also 1, and having it multiplied, you get 0.2. And for the transformer 2 new, so again we have 0.06 and 100 over 40, 220 over 220, so the old is 220 and the new is 220, so that's 1, squared it, and you multiply it, and that is 0.15. For the 3 transformer 3, you have 0.064 here, and you get 0.16. And for transformer 4, you have 0.2. For the motor, you have the old per unit X XPU old, you have 10.5%, which is 0.185, and the new apparent power, yes, we have selected the 100 MVA, that will be the new, divided by the old. What is the old? So the old is here, 66.5 MVA. And for the voltage, the old is 10.54, it is here. And the new voltage here, which we have chosen for our base new, that is 11 kV, so we divide it by 11 kV squared. So if you perform operation here, you'll get 0.255. That will be the new per unit X of your motor. So, and we are now here. We also want to get the transmission lines. To be able to do that, for the line 1, we have here 48.4 ohms. So we use this formula that the impedance base is equals to the voltage base squared divided by the apparent power base. We know that our voltage base here in line 1 here, we have 220 kV, so that will be the value squared divided by what is the apparent power base. It's 100 MVA for the whole system, so that's it. So you divide the squared of the voltage base divided by the 100, that will be 484 ohms. Now we use the per unit, which is equals to the actual over the base. So what will be the actual? The actual is actually the 48.4. Then the impedance base, this is what we have already computed. We using the chosen voltage and apparent power base. So that is 484. So 48.4 divided by 484, that is 0.1. Impedance CP unit in line 1 is 0.1. Now the same way we use it in line 2. Again, in line 2, the voltage base here is 110. That is what we choose. Also, the apparent power base is 100. So 110 squared divided by 100, that's 121. So using again actual over base, so we get the per unit impedance of line 2, that is 68.43 for actual, over 121 for our base. So that is 0.565. So that is for the transmission line. So what remains now is the load. For the load, so again, the apparent power of the load per unit, use again the actual over the base. So what is the actual? The actual is 57 MVA. For the base again, we have already chosen 100, so that is 100. So you divide 57 by 100, that is 0.57 per unit. That is the apparent power of the load. But we are to get the impedance because we are using here the reactance diagram. So we need the impedance of our load. So to be able to get that, we know that the impedance of the load is actually a B per unit squared divided by the apparent power of the load conjugate. Okay, so this will be the working formula to be able for us the impedance of the load of the load system. Okay, so what is the voltage per unit? At the voltage per unit, again, we use the voltage here is 11 and it is divided by 11, which is the again the actual and the base. The actual is 11. It is not given here, but it is attached to 11 kV. Also is 11, so that is 1. So our voltage per unit is 1. For our apparent power load conjugate, we have now solved the per unit, which is 0.57. So we use it here. The angle is cosine inverse 0.6. It is given here as 0.6 according to one power factor leading. So this is more capacitive. So it means that if this is capacitive, angle should be negative theta or negative angle. It's because it is leading. If it is lagging, it should be positive. Okay? We know that when we have a negative angle for the load, it is a leading. It is more capacitive. If it is positive, then this load should be lagging, but it is leading, so this will be negative. But according to the formula conjugate, it means that we are going to take the conjugate of the negative value, so that becomes positive. So we put here positive cosine inverse 0.6 because it is conjugate. Doing a calculation, we get the impedance value of the load, which is 1.0526 minus 1.4035. Okay, so we now represent everything from this single line diagram to this reactance diagram, knowing that we have already found the per unit values. So for our generator, we have this one. So generator, the generated voltage. So what is the X here? We have already solved that it is 0.2. So we place it 0.2 and a bus bar. And then for the T1 and the transmission line and the T2, which is the transformer 2. So for your T1, we have already found the per unit. New per unit is 0.2. We place is 0.2. For the transmission line, we have here the impedance per unit, which is 0.1. And for the transformer 2, which is 0.15. And then a bus bar. Again, this second line, we have the transformer 3 here. Transformer 3 is 0.16, so we write it here. And for the line 2, we have 0.565, so we place it here. And then for the transformer 4, we have 0.2, place it here. And then a bus bar. Then the motor. So this is the motor. So what is the value of the motor? We have already solved for that, and we get the motor X per unit new is 0.255, so we place it here. And then the motor voltage. And then for the load, we have also Z, which is 1.0526 minus J 4035, so you will place it here. So we have this new diagram. We are computing for the new per unit value, so we can now use this for our analysis. It can be a load analysis or a short circuit or whatever that you can use it. You will notice that you are using here a small value because per unit is very small compared to the actual value. So that's it. Thank you.